Hey everyone, thanks for joining us for the next episode of our Python and AI series, Vector Embeddings. My name's Anna. I'm an event planner for Reactor, joining you from Redmond, Washington. Before we start, I do have some quick housekeeping. Please take a moment to read our code of conduct. We seek to provide a respectful environment for both our audience and presenters. While we absolutely encourage engagement in the chat, we ask that you please be mindful of your commentary, remain professional and on topic. Keep an eye on that chat. We'll be dropping helpful links and checking for questions for our presenter to answer live. Our session is being recorded. It will be available to view on demand right here on the Microsoft Reactor YouTube channel. With that, I'd love to turn it over to our speaker for today. Pamela, thanks so much for joining us.
Hello, everyone. Very excited to be here, as always, for our Python plus AI series. So for those of us new to the series, we are doing a 6-part series. We're doing it both in English and Spanish. So if you want to join for the Spanish version, Gwyn will be giving it later today in about 6 hours. So we can link to that in the chat as well. But we'll be covering all these topics in both English and Spanish over, the next month. And today we're on our second topic of vector embeddings. We already covered LLMs. If you missed that one, you can go back and watch the recordings. We will always be recording all these. You can just hop on YouTube right after and you'll be able to watch them. So if you miss anything, no worries. Just go back. You can grab the recording. You can grab the slides. It'll all be available for you, all the code, everything available. So welcome to the series and register if you have not yet. Today, we're going to be talking about vector embeddings and going really deep into them. And they are a really hot topic and also just really, really important, really cool technology. And it's just a really fun topic. You can grab the slides from this URL that we'll put in the chat. Slides are PowerPoint, so you can follow along with the slides if you want. You can download them. You can deliver them yourself. If you want to give a talk about vector embeddings, just do whatever you want with those slides. They're there for you. So today we're going to be going really deep into vector embeddings to try and give you a very good understanding of them, like a very good intuition for them, like understanding the difference between different embeddings, like why sometimes we use ones for the other, why sometimes they look different, different optimization techniques like quantization and dimension reduction. So we're becoming quite a lot today. We do also have the live chat. So if you have questions, you can ask them in the chat. I don't know how much time I'll have to answer your questions in the chat, but other people might answer them. And if we don't get to them, there's also office hours later today. So I'm happy to answer questions in our Discord office hours too. So let's talk about vector embeddings. Now, all of the demos for today's presentation are in this GitHub repository. So we're going to put this URL in the chat, and I'm going to show you how you can follow along if you want to follow along. So I'll go to this URL here and open it up in my browser. All right. And so here it is. So what I do is I'm going to click on code, and I'm going to create a new GitHub code space. So a GitHub code space basically is going to open a VS Code in my browser, and it'll actually have my VS Code settings in it as well. And so here, since I use light mode, it's opening up in light mode. So it's opening up VS Code, and it's opening this repo in the VS Code. And it's going to have it set up with all the requirements already installed in here. So this should make it really easy for you to follow along, is to open it in GitHub code spaces. All right, so that is all open. That opened pretty quickly. And so you can see the README, and we can see lots of notebooks on the side, and the notebooks are what we'll be using today. So you are welcome to follow along in GitHub code spaces if you would like. And you can also just do this afterwards too. So what are vector embeddings? So an embedding takes some sort of input. A lot of times that input is text, but it could also be an image, video, audio, like it could be all sorts of things depending on the model, but it takes an input and then turns that input into a list of floating point numbers. And that list will have different lengths depending on the model, right? So here I've got this table of popular embedding models that you may have heard of, right? So, one of the original embedding models or embedding algorithms was word2vec. And I actually remember using that like 10 years ago. And word2vec only embeds one word at a time. So you would pass in like the single word dog, and then you get back a vector, usually a vector of length like 300. And you can easily train your own word2vec model. So I've actually, gone through tutorials about, making my own word2vec model. So that was an embedding model that people used for, for like the last decade. But then we started having embedding models that could handle much larger inputs, and that made them much more useful. So one of them that's open is called SBERT, which you can use from the sentence transformers package. And that takes words up to 400 words, and then outputs vectors of length 768. And then we have the OpenAI models, and this is how most people have gotten to hear about embedding models, is because of the OpenAI embedding models. So the first one they had was the text embedding 8002, and that's still what a lot of people are using. And that takes text up to 8,191 tokens. If you remember from the LLMs talk, earlier this week, we talked about tokens. So a token is how LLMs break things up. And it's also how these embedding models break stuff up, right? So a single word sometimes will be one token, but other times it may take 2 tokens, it may take 3 tokens, it depends on the word. So that takes, quite a lot of tokens it can fit in. And then it outputs vectors of length 1536. Then OpenAI came up with their new embedding models, and this is the text embedding 3 series. And they came up with 2, a small one and then a large one, with the large one being the more capable one. And you can also see that the lengths, right? So the small defaults to outputting 1536, like that ADA one. And then the large outputs 3072. Now, both of those can actually be reduced. We'll talk about being able to reduce the vector length later, so don't worry about that for now. But their default size is 1536 and 3072. And then finally, Azure AI Vision, that's an example of a multimodal embedding model. And we'll actually talk about that in our vision models talk in a few weeks. And that can take image or text, and then it outputs vectors of length 1024. Now you're looking at all these embedding models and going like, well, which one do I choose, right? There's so many options. They're all so different. Well, one thing you can do is look at this leaderboard. This is from Hugging Face, and the leaderboard, tries to rank all these models according to different benchmarks. And so here, and this is really, really cool. You can see all these different options and ways to filter it, right? And so you can look and see like how it does for different, different use cases like retrieval, right? Like if you're doing RAG, you want one that's really good for retrieval. But you could also look at, I think they might break it down in terms of language support too. So you could do languages, right? So, if you're trying to, have really good performance for a particular language, and these are not the usual language codes, but presumably we could find the language you're interested in here. So you can check out that leaderboard. For me, I'm currently preferring to use the embedding 3 large. It's the most powerful of the OpenAI models, and might as well use the most powerful one. So we are gonna dig into these a lot deeper. So this is just an overview. It's a question like, what do these numbers represent? Yeah, so when we encode it in this list of numbers, it's representing a vector in this multidimensional space. And you can think of that space as being like, like a brain, like it has all these different concepts in it, and all the different concepts are like, represented. And some of them are like more similar to others. Some of them are farther away from others, right? So, a lot of times dog is going to be pretty similar to cat. So if you looked at those 2 vectors, they'd have a lot that were similar. But dog is also, similar to, animal in other ways, right? So you can think of it as a similarity space, a multidimensional similarity space that's trying to represent, all the ways things are related to each other, but you can't like look at an individual dimension and say this dimension represents this, right? So that's why it's gonna be a little tricky, because you're just looking at a bunch of numbers, right? How do you understand them? So the way that I understand them is by looking to see at like what the similarity space looks like. So don't worry, we're gonna dig in and see that, right? So first, how do we generate embeddings using one of these models? So for today, we're gonna be using the OpenAI models, and I'm gonna be using them with GitHub models because GitHub models are free. And so any of you can use those in the code space. So if you've opened the code space, then you can go to the repo and go to this generate embeddings notebook here. All right. And let me make sure we get this big. Okay. Generate. Okay. Going back. Okay. All right. So let me select my kernel, Python 3.12. All right, and then I can run this code here. So it connects to GitHub models, and it passes the API key. It passes the GitHub token as the API key. So when I'm in GitHub spaces, code spaces, I always have a GitHub token set in the environment. It's just set automatically by GitHub code spaces. So that means when we're in code spaces, this will just work, which is great. We'll be using the embedding 3 small model for this one, and then 1536 dimensions for that model. So for every model, you do have to know the number of dimensions. Then we can go down here and use the OpenAI package to generate an embedding, right? So we say this is the model, those are the dimensions, and then here's our input, and then we get back the output. So here I can run this, and we can see it's got a length of 1536, and then here is the vector, right? It's quite something. You can see like it's just a lot of floating point numbers. You can see it's a mix of positive and negative. If we go and do another one, and these are multilingual models, so we can write all sorts of things as long as we have valid Python, right? And then we get a different output. And you can't just look at the output and see like, oh yeah, like this one's different from this one, right? Like it just looks like a bunch of, a bunch of numbers when you look at it. But I have come up with different visualizations that we can use in order to understand them better. Okay, so let's look at vector embeddings across models, right? So imagine we take the word queen, okay? And we take queen and we send it into several different models, right? So the first thing we can do is send it into a word-to-vec model, right? And that one's going to output 300 dimensions. And this graph here is looking at each of those dimensions, right? So 0 to 300. So we can see the range is like from negative 0.5 to positive 0.5. And like, it's basically just, but between negative 0.5 to positive 0.5, it's just all over that range, right? Like it's a good distribution across that range. So that's what a word to vec, a standard word to vec vector would look like. Then I send it to text embedding Eta002. This is a really weird model. I got to tell you, it's a weird model. This has like just so many weird things. So it outputs 1536 dimensions. So you can see my graph here goes from 0 to 1536. And, I'm trying to show all the values here. And you can see it's like mostly really small negative or positive numbers, like around negative 0, point. You can see these numbers. They're really, really clustered around 0, right? So a little bit less than 0, a little bit more than 0. And then the weird thing is this spike right here. You see this? This is dimension 196. And in every vector that I tried with Eta002, dimension 196 was this huge spike. And I don't know why. It's something weird about this model, the way it was, the way it was created, the way it was trained, is that every vector ends up having a spike at dimension 196. So this is a weird model. And it means like if you're going to do something like, like normalizing these values or something, you have to keep in mind that they're not well distributed, right? Like most of them are right around 0. And this one has a huge spike. So I always found that really weird. And then I wanted to see, well, what about the new models? Do they still have this weird spike? So we look at this one, text embedding 3 small, and this looks way more reasonable. Like if you look at this, it looks kind of more like Word to Vec, where everything's nicely distributed and there's no weird spikes, right? So we go, we've got values between like 0.10 to negative 0.10, and they all, are kind of well distributed around that 0 line. So this looks way more reasonable. You still see there's a big difference in the range of the values, right? Like Word to Vec, it's got a much bigger range of the values from negative 0.6 to positive 0.5. And this one's still only negative 0.10 to 0.10. So that's why you get, like, the important thing is that you shouldn't be thinking of like absolute values for any of these things. It's all about within that similarity space, with all of the aspects of that similarity space, how similar are things to each other within that space. And that's also a good time to point out that if you are doing embeddings and using embeddings for similarity or search, you have to use the same model across everything, right? Because all of these models are different. They're all their own unique models that have different dimensions in different ranges in those dimensions and different similarity spaces encoded in those dimensions. So you need to know exactly what model you're using and what the dimensions are, and you have to be consistent with it because these are very different models. So what is the point of vector embeddings? Well, they're actually really exciting because once we have embeddings, we can start to measure how similar two things are within that embedding space. And there's different ways of measuring, and we're actually going to dig into different metrics later. But the most common one that you'll hear about is cosine similarity. And you can think of that like measuring the angle between two vectors in a multidimensional space, right? So if two vectors are the same vector, you would have, they have high similarity. And if two vectors are very different from each other, then they would have low similarity, right? So, just think about, all the vectors and how close they are to each other. So we can also try and look at the similarity space across models, right? Now you can attempt, like here, I'll show the code for this. Let's see, similarity. Okay, so here, so what I've done is that I took the 1,000 most common English words and I generated embeddings for them. So I'll show you the embeddings. So we're doing like this one. It's kind of a large file because it's got a bunch of embeddings in it. But yeah, so I took the most common English words and generated embeddings, and so that we already have those. So here I'm loading in embeddings from A to 002 and then embedding 3 small so that we can then, look at both of them. This is a function for calculating cosine similarity. There's many ways you can calculate it. You could also use NumPy, which would be more efficient. Here, I decided to avoid NumPy just so I could show you what it would look like with just Python itself. But if you're actually going to do this in your program, you would want to use the most efficient thing possible, which is usually NumPy. And then once we have that function, then we can look at compare two of them. And remember, we need to compare within the same model. If you ever accidentally compare across models, then it's basically meaningless, right? So if we look at dog and cat, we get a cosine similarity of 0.60. Now, here's the thing. You can't look at 0.60 and know that 0.60 means very similar or not very similar, because it depends like what it is relative to other things, right? Like what if we do dog to time, right? How similar is dog to time? 0.26, right? So what we see here is that dog is definitely more similar to cat than to time. So what matters is the relative similarity, right? So dog is more similar to cat than time. What about animal? 0.68. So dog is more similar to animal than it is to cat, right? What about queen? Are dogs queens or kings? Let's see, 0.37, right? So what matters is the relative similarity values, not the absolute. Okay, so now we can look at, so, once we have this ability, then what we could do is, for a particular, word, we could find all the 10 most similar words, right? So we can do this with dog and say like, okay, what are the 10 most similar words to dog? And here we can see the most similar in this set of 1,000 words is animal. And then God. Okay, so why is God so similar to dog? All right, so this is for ADA002. Remember, ADA002 is a weird model, right? I'm glad we've moved on past it because it had weirdness like this, right? So what we see here is that it thinks that dog and God are actually very similar. And maybe some of you are dog people. I'm not a dog person. I don't think they're similar to God. But I assume that the reason that this model thinks they're similar is because this is also encoding spelling information. So this model isn't thinking of just about semantic similarity, like, dog and think about a sentence and what you could fill in a blank. You could put dog in the blank, you could put cat in the blank. You couldn't put God in the blank a lot of the time, right? But from a spelling perspective, they actually are similar. And so maybe sometimes we get typos like that or something like that. So my theory is that the embedding ADA002 model was also encoding spelling issues in its space. So we see dog similar to God, also similar to drug, right? And gun, right? So, that's weird. So remember, this is ADA002. Dog, help us all. That's good. So now let's look at ADA, the new ones, embedding 3, right? And now it's looking really good, right? Dog, animal, horse, cat, boy, man, child, bird, door, baby. All right. I mean, things got maybe a little weird at the end there, but it's only got 1,000 words to pick from, right? So we'll let it go. But this looks much, much more reasonable, right? So already, I have more confidence in the new embedding 3 models when I, look at stuff like this and be like, okay, it definitely looks like it's encoding more semantic similarity, while this was encoding both semantic similarity and spelling similarity. Yeah, I see you're all coming up with theories as to why they're similar. If you ever figure out dimension 196 or any of this stuff, please do ping me and let me know. You dig into the space. All right, so now what we could do is we can attempt to visualize the similarity space too by reducing the dimensions, but it's really a severe reduction, right? Because we're going to go from 1536 to just 3 dimensions, right? And we're going to use this technique called PCA, Principal Components Analysis, and this actually can take a little bit of time. Well, that one was pretty fast, but and so what I'm going to do, I just took 10 words here, right, and then plotted them so we could see how close things are. And this is ADA002 where dog and God are somewhat close, but here you can see it's everything's kind of close here. So I actually don't think you should put too much stock in this visualization that I attempted here, because it's really hard to take 1,536 dimensions and reduce them down to 3. Right. So I think you just basically shouldn't pay attention to anything like this. It's kind of fun, but it's really not going to tell you how your space is going to work out. So it's cute, but don't do it. Okay. All right. So moving on. The other thing that's useful to look at is what is the range of similarity values for a model? Because that can give you better intuition that when you do see a similarity value, what it means. So what we're going to do here is plot. For every word, I'm going to plot its similarity to every single other word and then make a graph of it, right? So this is for dog again. So I'm going to check to see for the word dog, what is the similarity, the cosine similarity for dog to every single other word. All right. So we can see for ADA002, once again, ADA002 is a weird model. The similarity values range between 0.89 and 0.7. And they don't go beyond that, right? So we never see similarity values with less than 0.6, and we never see them greater than 0.9. And that means everything's really clustered. So once again, when you're using ADA002, you can't it's hard to look at the similarity values and just know oh, that's similar, that's not similar. You have to look at the relative values. Now, when we look at text embedding 3, this is 3 small, we see a much more reasonable range, right? So the values, most of them here were around 0.3. So that's kind of not that similar, not that dissimilar. And then we see it going up to 0.7, 0.8, and then going down to 0.1. So you can even like look at some of those values and get an idea for like whether, like, oh, does this mean it's very similar or very dissimilar? Like if I see 0.1, okay, that's dissimilar. If I see 0.7, that's pretty similar, right? And then if it's around this middle here, like, well, it's, kind of in the middle. So this is a a nice range. Okay. So hopefully that's giving you an idea for what these similarity spaces look like more better intuition. Now, these examples were all for single words. But of course, with these models, we can encode really much longer things, right? Up to 8,000 tokens. So what I've done is encoded Disney movies because we're a Disney family. Let's see, what did I do? So this one, so I think I encoded like 500 Disney movies maybe, right? So you can see here's the movie title and here is the embedding. So it's only encoding the title. It's not encoding, description, anything like that. It's just the title. But these titles are pretty well known, so it should be interesting. So we can load that in here. And so then we can, look at a movie that's in the set. So 101 Dalmatians, and we can say like, hey, how similar is this movie to all the other movies, right? And we can see the most similar one is to 101 Dalmatians is 102 Dalmatians. That makes sense. That's pretty good. And then after that, we have the Aristocats, also one we like. And then a bunch of things about cats and dogs. So this all makes total sense. And this is with the, the new model. And so the similarity values are all nice values here. So we can see even like Lady and the Tramp, that's fairly similar. It's a movie about dogs. And that's 0.427. So that I would still consider really similar. So you can already start to get an idea for how you might use vector embeddings, because with vector embeddings, like I basically already have a recommendation system here, right? Like I could put this on a movie site and just say, hey, you liked 101 Dalmatians, consider these other movies. And it would actually be fairly accurate. There's ways of making it like way more accurate. Like we should probably look at description and we should look at like what other users watched and all that stuff. But as a first approximation, like you can actually get some pretty good recommendations just based off of similarity of vector embeddings. And that's part of what's really exciting about vector embeddings is that we can easily build recommendations without having to worry about, getting lots and lots of user data, depending on what we're building recommendations for. Here, it's recommendations for Disney movies, and the vector embedding models already know about Disney movies, right? You could also, in theory, build your own embedding models for your own space. Okay, so then we can and you can what do you want me to search for here? I think we have Moana in here. Let me try Moana, right? So Moana thinks it's most similar to Mulan, we've got the female heroine who's saving the day, Lilo and Stitch, Little Mermaid, right? You see similarities there. What's another one that we like? People always want me to do, what is it? The Emperor, what's the Emperor one? The Emperor's, oh, I got to figure out how to spell it. It's like Emperor's New Groove, right? Emperor. Oh, those are the words. Let's see. The Emperor's New Groove, that one. All right, let me look at that one. People like to see this one. We got to escape that apostrophe. Okay. All right, Emperor's New Groove is most similar to a Goofy movie. I love a Goofy movie. It's actually one of my favorites. So I probably should watch this one. And some other ones here. All right. Yeah. So when you see this, I see questions about the similarity values, right? So here you can see there's a similarity of 0.483. Whereas when we did 101, so here the most similar one is 0.83, right? Whereas when I did 101 Dalmatians, we saw 0.887, 0.540, and then we started going into the 0.4s. So you might say one thing you can do is come up with an idea for what you consider to be a strong signal similarity, and you could do cutoffs, right? Depending on what product you're building, right? But there could be a point where you say listen, we know that everything below 0.4 is really not that similar, so we're just not going to use it. That is possible to do once you have to have a really good understanding of your similarity space. Like you got to do like a lot of checks to see like what the rate, like what the values are that you're getting. And it's going to be, of course, specific to the model, right? So it is possible to do like a similarity score cutoff, for certain use cases that might make sense. But you need to really do a lot of checks to see what the ranges are and at what point you feel confident saying like, yeah, we're going to cut off everything that's, less than this value. Because it's interesting, like even for 101 Dalmatians, I actually think all of these are good recommendations, right? Because also the thing is like some things just are more similar to other things, right? And just have more things in the data. So yeah, it's a little tricky to do a cutoff. I would say it's hard to do a strict cutoff with vector embeddings. When we talk about RAG, we'll talk about ways of like really improving the retrieval when you're using vector embeddings, using other kinds of models. So you can try to come up with a cutoff, a threshold of similarity, but it is really tricky. So, don't do it lightly. We can also do the least similar movies. These are a bunch of ones that I mostly have not heard of because I only watch cute animal movies. Okay. All right. So that was our dive into similarity. And as we talked about different business use cases, so I have, some examples here. So you could build the recommendation system like we talked about. And this is a nice article on the Postgres, in the Postgres documentation about how to do that using PostgreSQL, if you like that database. And then another thing you can do is fraud detection. So there's there's existing databases of fraudulent, messages and emails and all that stuff. And what you can do is like measure and see like how similar is this new thing that I've gotten to the fraudulent things. And if it's really similar, well, then it's very likely to be fraud. You can do the same thing with spam, right? Say like, okay, here's a bunch of spam emails and their scores, and also here's some not spam emails. Is this thing closer to spam or not spam? And this is where you do have to come up with a cutoff, right? If you're going to do fraud detection, spam detection, you will need to come up with a cutoff. And you want it to be like a pretty clear cutoff, right? Because you don't want to, mark something as fraud that's not fraud. But this is a very commonly done thing. So definitely if you're interested in fraud detection or spam detection, you can look into using vector embeddings to do that. And there's a nice blog about it here. Yeah, and I see the question about the similarity to the movies. I only embedded when I generated these embeddings, was only based on the titles. So, is it based off the plot or whatever? Like in the brain of the similarity space, probably they saw these titles next to the plots a lot. And in that case, in some ways it is including the plot, right? Because of where it happened to take place, where it was next to all the time. But I only, I only did the embeddings for the title. If I was actually going to do this for a movie recommendation site, I think I would also bring in like a 2-sentence abstract, and I would embed all of that into a single embedding, because then I think you'd get better results, especially for ones that have like shorter titles that are more ambiguous, right? Like these ones are all like really distinctive titles, but like Mumford, like that's, or Phenomenon. Right? Phenomenon, you're not going to get great results for that as a movie, because that's, that is also just a word. So if I was going to really build this for a movie recommendation, I would have both the title and at least like a 1-sentence abstract, maybe genre, right? So that's the thing, you can like pack whatever you want into your embedding. So you can do like title, 1-sentence plot summary, genre. That's probably what I would start off with. Okay, now let's talk about what everybody talks about with vector embeddings, which is vector search. So, once we have all of our data encoded as vectors, the exciting thing is that then we can take any new data and compute an embedding vector for that new data, that input, that user query, and then find the closest vectors for that query vector, right? So if we get like tortoise and we're searching animals or something, right? We can search all of our existing vectors and, find like snake and frog, right? Or, in my Disney movie list, I could search for non-Disney movies and see which things are most similar to non-Disney movies, right? So let's go ahead and dive into the search notebook. So here I'm only going to load in the embedding 3 small. I think at this point you've seen that the embedding 3 models are really good, much better than the ADA002. So that's what we'll be using going forward. And then I'm going to connect with GitHub models. Okay. We have this function that generates embeddings. Okay. So now here I've got the cosine similarity function from before. And then I have this, what I call an exhaustive search function. So exhaustive search means that you are going to check, you're going to compute the cosine similarity of the query vector to every single other vector. So we are exhaustively searching the search space to find exactly which are the most similar. And so then to use that, we're going to generate an embedding, right? So we say like, oh, a toddler-friendly movie about cats. And then we do the search. And we find the 10 most similar, and then we display them. So you can actually see I already did this search here. So a toddler-friendly movie about cats, we get the Aristocats, and then the Tigger movie, and then Ratatouille, cats, rats, similar. Cars too. That's where things get a little different. I don't know why Cars 2 ranks so high, probably because it's toddler-friendly. All right, so let's try. All right, what do we want to search for here? Let's see. Yeah, The Matrix. Movies that are like The Matrix, but for kids. I don't know. Oh, I probably didn't. Let's see. What am I missing? Add credentials. Let's see. All right, let me just refresh my. Oh, because I'm local. Sorry. Let me do this in the locally. I can do this with Azure locally. All right, let me do this with Azure. I have this open both in my local VS Code and in code spaces. And locally, I'm using Azure, and code spaces, I'm using GitHub models. All right, so now I'm going to run this. This will use the Azure connection. Okay, movies like The Matrix, but for kids, we got The Kid. All right, so it really over-indexed on kids. Honey, I Shrunk the Kids. Okay, I didn't want movies about shrinking kids. I guess that is kind of Matrixy though, because like they're like in their own little world. Tron, Mars Needs Moms. I've never heard of that one. But yeah, we can enter in anything in here. So this is cool. Is once you have vector embeddings, then you can start to support searching and being able to find things. Now you'll see like sometimes it'll work really well. The other thing is like we can do it in other languages, right? Like películas, and I'm not even do the accents right, but sobre leones. Okay. Okay, and we get the Lion King, and we get Lion Witch in the Wardrobe, right? African cats, yeah. So this is what get people really excited is that when you have vector search, suddenly you can, when you have vector embeddings, you can suddenly have a search, and that's it, right? Now I have to warn you that vector search is not going to solve all your problems. You really want to have keyword and full text search as well. You also want to have semantic ranker, which got mentioned in the chat. We are going to talk about how to do really good search in the RAG session that's coming up next week. So definitely come to the RAG session. We'll implement a full hybrid search with ranker, in Python, so you can see what I mean. But this is what gets people really excited is that, with just vectors, we suddenly have the ability to have at least a basic search. So you can definitely start with vector search, but as we'll talk about in the RAG one, a lot of times you want to go beyond vector search in order to really get really good results. Because what you saw is that some of these results were really good, right? Like these ones, were really good. But when I asked about, like the Matrix one, like those results were kind of nonsense, right? So you want to know, like, okay, like vector search can help you find the things that you weren't finding before, but it can also be really noisy, meaning that it gives you results that you really don't want to have. So we have ways that we can avoid those noisy results. All right, and now, so that was an exhaustive search, right? So, exhaustive search is great because you're going to find every single possible thing and figure out exactly which is the closest. However, if you have like millions and millions of vectors, you can't do an exhaustive search. It would just take too long, right? And so many like production databases are going to have millions and millions of vectors. So what we do instead is called an ANN search, approximate nearest neighbor. So this is an algorithm that uses some sort of way of splitting up the search space, some sort of heuristics in order to speed up search time. The most popular one these days that you've probably maybe have heard of is HNSW. That's the one that's well supported across a lot of places. So it's supported by the PG Vector in Postgres. It's supported by Azure AI Search, ChromoDB, Weaviate, right? So you'll see it all over the place. We can also use it directly from Python. So let's actually use it from Python now. So here I import HNSWlib. And I set up an index. So whenever we're using one of these approximation algorithms, we have to make an index, and that index is going to be, tracking the vectors in some way that makes search faster, right? So it's similar to a database when we make indexes for our databases to have more efficient queries, right? So we make an index, and we initialize the index, and there's some parameters here that I won't go into, but there are some really good YouTube videos from Pinecone actually about these parameters if you want to learn more about that. But we initialize our index. We add in a bunch of all of our items here. And then we can do, then we've got our index set up. So this is just it set up, and we can keep adding more stuff to the index as we got more stuff. And that's what's great about HNSW is that it's pretty good for adding things, right? That's why lots of people are using it, because HNSW is fairly fast at adding new things to the index. Other algorithms aren't as good at adding new things. And then we can search, right? So here we search, and we get, pretty much the same results as we got with that exhaustive search, right? And in this case, it was probably about the same speed. But if we were doing, billions of vectors, we would really see the difference between exhaustive search and HNSW. Now, most of the time, you're not going to be writing this code, because most of the time you're going to be using a database that has implemented this behind the scenes, right? So this was actually the first time that I even wrote this code, because I'm always using a database instead, right? So I'm usually using PG Vector and making an HNSW index, or I'm using AI Search, which always uses HNSW, right? So you shouldn't expect to see, to be writing this code yourself in most cases. Instead, you should be expecting to configure this with your database of choice. I see some questions like, with these parameters, can you change them after the fact? It depends on the database. I think most times you can't, but that's a good question. I don't know, because normally I know, like with PG Vector, we declare it at the beginning. So I've never tried changing the parameters after the fact. It's a good question. Not sure. Now you might also hear of disk ANN. That's what's used by Cosmos DB now. It was actually came out from Microsoft Research, so it's like a very efficient I think it takes advantage of your hardware to get really efficient embeddings. So some Microsoft products are using it now, like Cosmos DB. There's IVF Flat, which is supported by PG Vector. It doesn't work as well when you want to add new data, so that's why most people aren't using it for a lot of these use cases. And then there's FICE, and FICE is in memory only, so you don't see it in a database. But we will use FICE for the RAG talk coming up, so we'll get to see that here. So keep these in mind. HNSW, disk ANN, those are the ones you're probably going to see. And if you want to dig more into them, there's lots of there's research papers, there's tutorials. My favorite way of learning about them is the Pinecone YouTube videos. They have a really good developer advocate that does great talks about them. So that's what I suggest if you want to learn about HNSW and how it actually works. It's pretty interesting. So what is the business use case for search? Well, the big really one is RAG, where people are, making it easy to have LLMs answer questions based off of your own data. And so in RAG, first we do a really good search, and then we pass those search results off to an LLM. So as I say, we're going to talk more about that in our upcoming session. Okay, let's talk about vector distance metrics. I need to start going faster because we only have 15 minutes left, and we still have 3 more things to talk about. So we've been using cosine similarity this whole time. There are actually other ways that you can measure the distance between 2 vectors. When in doubt, use cosine similarity. It's going to work with basically most of the embedding model, all the embedding models. But it's good to know that there are other ways out there too. Now, what metric we pick depends on whether the vectors are unit vectors. So here we need to go back to, for me, which is like probably high school math, right? So a unit vector is a vector with a magnitude of 1. Magnitude is like the length of the vector. And this is how you can calculate the magnitude of a vector. So here, these ones are not unit vectors. You can kind of see in the graph that they're about a length of 3.7, right? So these are two vectors that have the same magnitude, and that magnitude is, about 4. Now, we can make these into unit vectors by normalizing, and so they look similar, but now these two vectors have a magnitude of 1. Okay, so these are unit vectors because their length is 1, right? If you kind of look on the graph, you can imagine that the length is 1. Okay, so that is what a unit vector is. So we'll just keep that in mind because it does affect which metrics we can use later. All right, so we've got 4 different distance metrics. The first one is Euclidean distance. This is the straight line distance between 2 points in Euclidean space. You can just think of it as the bird's fly distance, right? So if a bird flew from the end of one vector to the end of the other vector, what would the distance be? That's Euclidean. Now, I don't actually know what use cases we practically use this for, but most of the vector search algorithms do support using it if you need it. There's also Manhattan distance, which is, you think of this as if you need to like take a taxi between 2 points in New York City, you have to go down roads, right? So you can't do the bird's fly distance. You have to go down this road and this road and this road. So that's Manhattan distance. And you can, visualize it, going along each of the axes. And, once again, not sure when we'd actually want to use this for most modern uses, but it is supported by most of these indexes. Then we have dot product. So dot product is, I couldn't come up with a good way to visualize it. It's the sum of the lengths of the components here, right? So we sum them all up and we get the dot product. And we're going to use this dot product actually. So the dot product could actually be useful. So just keep this in mind. This is the dot product. And then we have cosine similarity. So the thing about cosine similarity, if you look at the math for it, it is dot product divided by the magnitude, the product of the magnitudes, okay? And the significant thing here is that if your magnitude is 1, then this denominator is going to be dot product over 1, which means that for unit vectors, cosine similarity is the dot product. They're actually they'll give you the same results, and you actually do less work because you don't have to divide by the magnitude. And also, you keep in mind here, there's a difference between cosine distance and cosine similarity. So cosine similarity is high when 2 things are similar, and cosine distance is high when 2 things are different, right? But they're just the inverse of each other. So if you ever heard both of those terms, they're just, you can see cosine distance is 1 minus cosine similarity. All right, so the big point here is that cosine similarity for unit vectors is the same as the dot product. And for some databases, that is useful to know because the dot product can be faster, right? So for PG vector, if you're using PG vector with Postgres, because of the way it's implemented, if you know you're using unit vectors, it'd be better to use dot product because you're going to get a faster response because it doesn't have to go through the extra effort of calculating the magnitude, right? So consider it. And the thing to know also is that all the OpenAI vectors we just looked at, they are all unit vectors. So if you are using, embedding 3 or 80002, you should be able to use dot product and see the exact same results as cosine similarity. So that's it. So I don't want to get too deep into the math because also I'm not that good at the math. But the point I want to get across is that if you are really concerned about performance and you are using unit vectors, which you are if you're using the OpenAI ones, then depending on what index situation and database you're using, you may want to look at dot product to see if you can get even better performance. All right. So continuing our talk about performance, we're going to talk about vector quantization, which is one way of reducing the size of vectors. So as we saw, our vector embeddings are floating point numbers. And what we can do is we can turn those floating point numbers into integers or bits. So scalar quantization turns a floating point into an integer, and binary quantization turns it into a bit. So let's see how this works in more detail, right? So scalar quantization. So we have this, list of floating point numbers. So what we do is we look at the min and max of all the embeddings, right? So we actually saw those graphs already. We saw like, oh, okay, like, this embedding goes down to negative 0.5 and goes up to positive 0.5, right? And then we take those and we normalize all the embedding values between 0 and 1 based off that min max. So we say like, okay, like this is what it would look like between 0 and 1. And then we can map those onto integer buckets from negative 128 to positive 127, right? So that then all of our values are within, can be stored within an int8 data type. So this is what's called a signed integer as well, a signed 8-bit integer. So this takes 8 bits to store the integer, and it can store from negative 128 to 127. So this is a huge reduction in how much space the computer needs in order to store these numbers, because floating point numbers actually require 60, this is float 32, but in Python, they take 64 bits usually, right? So floating point numbers can take a lot of space, whereas this is only going to take a byte, which is 8 bits. And so, you might, say, okay, what does that look like, right? So this is for Moana, right? So you can see, we start off with this vector here, and we go to this vector. And both of these have 1536 dimensions. But this one now has values between around like negative 20 and positive 80, right? So these are all now integers within this range. Now you're going to wonder, like, how does this affect, like, is it still going to work? Can you actually do quantization and still get good results? So I've done a very scientific analysis here of Moana with the similarity before and after. And what you can see that we mostly get the same similarity. A couple things switched, right? So we see like Little Mermaid and Lilo and Stitch switched, Maleficent and Ice Princess switched, and everything else stayed the same. So from this experiment, you can see really similar similarity values, right? And that's pretty encouraging that we can see such similarity values. This is a lossy process. I just saw that comment. This is definitely a lossy process. We have lost some information, right? Because we've gone from 32 to 32, here like 32 bits or even 64 bits to 8 bits. We have lost information, but the whole question is, have we lost so much information that we can no longer use the vector embeddings for what we want to use them for? And in this case, it still looks pretty good, right? It still might be good enough, right? So if we're trying to, store lots of vectors efficiently, we might want to consider this as a way of doing that without losing too much quality. But that's why you do want to have like actual rigorous evaluations, right? Not just this one Moana one. Like you actually want to be checking like, thousands of queries to see like, what do I get before? What do I get after? Is this acceptable? Now, binary quantization goes even more extreme, right? So here we take those numbers and they get mapped to either a 0 or a 1, and that's it, right? So what we do is we pick this, like we look at the center of that range, like, maybe it's like around 0 or something, right? And if it's less than the center, then it becomes a 0. And if it's more than the center, it becomes a 1. And the crazy thing is that this actually works. Like I was actually showing this to my mom. She was working out the math with me, and she did not expect this to work, but it actually still retains a lot of the information somehow. Like, so here, this is our visualization, right? Because afterwards we just get a bunch of things that are either 0 or 1, right? We still have the same length, 1536, but it's 1536 zeros or ones. Now, how does this affect similarity? So we can definitely see a big difference, right? Only 2 of them stayed the same, and then a bunch of them switched, and we lost Monsters University, which wasn't that good of a fit anyway. So it definitely does affect similarity. Like this, we've lost a lot of information. Once again, it might be good enough depending on what you're doing, right? So it's something to keep in mind. All right, let's look at the effects on storage size, right? In Python, storage size is actually going to not change because Python, the built-in number type always requires the same number of bits. But if we use NumPy typed arrays, then we can get a reduction in size when we go from float to int NumPy doesn't have a bit type, so we don't save with bit. But databases can pack the bits into a single byte, and they can save even more space. So for Azure AI Search, we've done more rigorous analysis with AI Search because AI Search does support doing this quantization. And there they can do bit packing, and you get a 96% reduction in space if you do bit quantization. Now, as you see, we did lose a lot of information, but AI Search does this cool trick where you can do this quantization and you do the search using the quantized vectors so that your search is really fast and your index is small. But then you can store the original vectors and rescore everything according to the original vectors. So you end up getting the exact same results. It is crazy, but it's cool. It works. I have an upcoming video that's coming out in next week that talks about it. So definitely tune into that video when it premieres. But it's so cool that it actually works. So you can like use the quantized ones for the search, but then you just grab way more than you need, like 100 results, and then you rescore them according to the originals. Really, really cool technique. Okay, dimension reduction. This is the final thing we want to talk about, and I did see this mentioned in the chat. This is another way of reducing the size of vectors, but this time we're going to reduce the dimensions of the vector. As opposed to like, how much space each number is storing, right? So the cool thing is that a bunch of the new embedding models have been trained in such a way that you can reduce their dimensions severely, and still it keeps a lot of the semantic representation. It's incredible that it works, but it does, which is really, really cool. So for like the embedding 3 large model, that has a default dimension of 3072, but you can truncate it all the way to 256. Now, you can truncate at 2 stages. You could either truncate when you're first generating the embeddings and say like, okay, I'm going to use this 3 large model because I like it, but I'm only going to generate 256 dimensions. So you can do that. Or you can truncate when you're storing in the database, if the database supports doing the truncation on the fly like that. So Azure AI Search does support it, so that then you can keep the originals at 3072, but then the index could store the 256, right? So how do we generate, how do we truncate with the OpenAI SDK? So we would just pass in dimensions, how much dimensions we want, and we can only do it with a model that supports it, right? So let's see here, right? So when I generated the embedding here, right, I could actually go and say like, oh, I actually only want it at 256. And as long as it's one of the newer models, the text embedding 3, then it should support it. So it'll go all the way down to 256. You can't go lower than that, right? So there we got 256. So that's how you can do it when you want to do the reduction while you're generating the embeddings. So I went ahead and I embedded for both 1536 and 256, and compared, and we're going to compare them and see how this affects similarity. So what we can see is that we before and after we do have some changes in the similarity, right? It's kind of reminds us of like the binary quantization. So some things switched around. We lost some things, like, some significant things here. But also, if you look at the results, like these are all still good results, right? Moana, Little Mermaid, like Mulan, like they're all pretty similar, right? So it might be okay to have this differences. Like this might still be reasonable to you. Now, so that's quantization. All right. So that's it. As is, the cool thing is that you can actually use both techniques. So you could reduce the dimensions and you could do quantization. And the cool thing is, once again, with Azure AI Search, you can do both of them only in the index while keeping the original vectors, and so that your index, your vector search is really fast, and then you do all the rescoring with that. And yeah, it's just really, really cool that it works. Let me I do want to show, okay, I have 1 minute left, so I'm just going to show it just because it's just so cool. I wasn't going to be like plugging AI search, but I'm just really impressed by this technology. So so here is my comparison, right? So this is the baseline with no compression, and this is for a question about first avian dinosaur in the fossil record, and I'm searching this Wikipedia data that I loaded in. And so you can see this is the baseline results, right? And here, this is when you both truncate and do scalar quantization, and this is binary and scalar, binary and truncation, right? What you can see is the results are actually exactly the same as the baseline, and that's because of keeping the originals and rescoring the originals. Now, if you discard the originals, the results suddenly become different, right? This is when you discard the originals and you don't rescore, and then the results come different. So anyway, I don't have time to like really dig into it, but you should watch that Ragtime Journey 3, and that's where we're gonna like really dig into that. But I think that's a really cool approach. So I know AI search has it. There might be other vector databases and search engines that also support it. It's very cool if you are concerned about performance and you needing to store billions of vectors. There's way more resources here where you can dig in. The best way to get these links is from the slides. So we'll put the slides URL in the chat again so that you can have these slides for you. And next steps, come to the upcoming streams. Our next one is on RAG, and we did talk a lot about RAG today, so I'm glad that's coming up next week. If you have more questions, I have office hours today in just 2 hours in Discord. So come to the office hours and come with your questions. I know there were lots of questions in the chat that we didn't get to because we had so much to cover today. So do come to our Discord office hours and ask your questions there. And if you want to get more Python AI resources, we've got this list here. You can put in your email address and get the resources, and you'll be also signed up for a newsletter. And there you go. And of course, Gwyn is going to give this same talk in Spanish in just a few hours. So if you want to hear it in Spanish, see it with Spanish examples, come to Gwyn's talk later today. All right. That's what we have today. Thank you, everyone, for coming and for engaging so much in the chat. And I hope to see you at office hours or at the RAG one. Bye, everyone.
Thank you all for joining, and thank you to our speakers. This session is a part of a series. To register for future shows and watch past episodes on demand, you can follow the link on the screen or in the chat. We're always looking to improve our sessions and your experience. If you have any feedback for us, we would love to hear what you have to say. You can find that link on the screen or in the chat. We'll see you at the next one.